First, let me say this is fantastic. It's really exciting to see this conference on this subject and this many people involved. And yeah, I don't know, really exciting. I mean, it's funny because I've been doing, well, okay, so I made a con lane when I was like in first grade. I don't know what age that is, like 8 or 9 or 10 or something. This is like kind of embarrassing for me to put on the screen because it really reveals, I guess, to some extent what may have been on my mind at the time, or just what, I don't know, what words. But, you know, part of this was just coming out of like, you know, children are mimetic. Anybody who has children, I don't have children, but okay, but like, children are like copy, oh, okay, I should be in the frame. Children really copy what they're seeing, and especially what parents are doing, what peers are doing. And what I did was, because I was in school and, you know, have these language textbooks, so I made a textbook for my language because I guess that's what you do. And yeah. For some reason my language was called Exodus. I really don't know why. I thought that was a really cool sounding word. I still do. Okay, so what I'm presenting here is a kind of conceptual project as a whole that I've been referring to as language machines. One of the language machines is the devices that you might have seen outside, and I will explain what they are and what they do. But first, I'll show you a video. Hopefully this one. Okay, what we have here is 4 little robots. Not robots in the sense that they move around, but they can detect changes in light and sound, light level and sound level. These are with their kind of exoskeletons on. They're presented to you in the nude here. Now, so they respond to experiences, to their experiences of the world, and they have words or names for those experiences, and they teach others, the others in their group, what words they have for certain experiences. And I'm going to explain how that works. Okay. So I have to remember which order of slides I have here. Okay, so first, I want to talk about emergence, language emergence, and I don't know, emergence in general. So let's ask.
Explain. Complex systems can sometimes behave in ways that are entirely unpredictable. The human brain, for example, might be described in terms of cellular functions and neurochemical interactions. That description does not explain human consciousness, a capacity that far exceeds simple neural functions. Consciousness is an emergent property.
In other words, something that's more than just the sum of its parts.
Exactly.
Thank you, Lieutenants David and Jordy, for that concise description. Emergence is the phenomenon that underlies things like this. This is an ant cathedral, okay? The ants don't have plans to build their cathedrals, all right? The construction of this whole, you know, relatively complicated and sophisticated structure is an emergent property of the actions of many very simple individuals. Similarly, crystal formation is also can be described as an emergent process. You know, water molecules don't encode the patterns for these larger patterns, but well, I guess you could argue in a certain sense that they do, but it just turns out this way. One of my favorite definitions of language is this: language is an accumulation of shared meaning, and I've found this to be extremely useful and I think extremely accurate. And what this really means to me, and the reason why I like this, is that language really has to do with the group of speakers, and that language is happening between speakers, and I use the word speakers loosely. It could be writers, it could be, you know, psychic thought transmitters. Actually, this project too grew out of an interest in trying to figure out what telepathy would be like if that existed, what that would even consist of, which is still an open question and a really interesting question. Okay, slightly tangential. So the only thing that links two signs together ultimately, at least in the way that we're used to with natural languages, is just people saying that they go together, okay? I mean, this was Saussure's whole insight, was that symbolic signs can be completely arbitrary and basically effectively always are completely arbitrary. And so this is really counterintuitive to a lot of people, I think. I mean, in my own experience, this is counterintuitive to a lot of people. In the history of linguistics, I think demonstrates that counterintuitivity as well. I mean, for the longest time, just people were like steadfastly refused to believe this. And so you had all kinds of competing theories for the origins of language, and a lot of people were fixated on like onomatopoeias as the source of the language and things like that. But ultimately, it doesn't matter. Like brains, these neural networks that we have in our heads, turn out to be fantastically good associators of arbitrary patterns. I mean, that is completely what the human brain is doing at all times. That underlies everything that we're doing. And so, you know, when we ask how do people know what words mean, what symbols mean what, it's through watching and learning, and that's what these robots do, the Dawn Chorus, as I call them. So here's a shot of the device. If anybody's into electronics and hardware, I'd be happy to go on at great detail about what this actually does later. Here's an overview diagram, just in case you're completely curious. Really, the big picture here is that they have senses, they have sensory capabilities, and they have an output capability. They can see light, they can hear sound, and very, very, very rudimentary senses. They can make sound, okay? And then they have one other kind of meta sense, which is this radio module. Each device has a radio module in it that allows them to transmit information between nodes. And the reason why I did that is because, like normally you would think you would have a mic, the microphone used here is not used to listen to their other words, to listen to the other words. It's just used to detect an abstract level of sound that really is ultimately just good for detecting whether it's quiet or suddenly loud. But doing having them listen for the other's words is really a whole project unto itself. I'm talking about having the microphone listen to the words. So instead of that, I'm transmitting their words through the radio. This is probably confusing, and it'll get clearer when I start to go into the deeper explanation. So this diagram is just showing that when this guy gets a stimulus, which could be a sudden change in the level of light and or sound, it's going to say its word for that experience at that time, that it has at that time. All of them start with random words. Oh yeah, and a word in this context is this short series of 4 tones, which you might have already heard out there, which sounds like that's what a word is in the context of these devices. So it's a 4-bit combinatorial space. They're able to put these different tones into 4 different positions. Actually, that's more than 4 bits. Sorry, but so it says its word for that experience. Okay, and then it also transmits that word via the radio link to the other ones. This is just to take place of the much more complicated task of decoding the actual acoustic signal. So instead, they're just transmitting that word choice to the others. And so this is the equivalent of if somebody shined a flashlight at me, I would say bright, and then you all were listening to me say bright, and you also saw what that stimulus was. That's what's being transmitted over the radio link to the other units, is the combination of what the experience was and what my word for that thing is. So every time somebody speaks in this setup, they are teaching the others what their word for some experience is, okay? So that kind of starts to bring us to the whole other part of this talk, which is about neural networks. Are there any neural network aficionados or hobbyists or experts in the room? Okay, I'm seeing this a little bit, which is perfect because if there were any experts in here, then I would have to make all kinds of caveats and explanations. But instead, you can all just take my word for it. Okay, so here's the problem. All right, what is this?
Chair.
It's a chair, not a trick question. Okay, what is that?
Chair.
Okay.
Chair.
Or woman.
Or woman.
Yeah, I don't know. And this?
Chair.
Yeah, well, so the question is how do we get a computer, or how do we how do we know that this is a chair, but we also know that these other things are also chairs? I mean, this chair looks like it could be, I don't know, like some sort of transformed spaceship.
Fuzzy logic.
What's that?
Fuzzy logic.
Yeah, well, fuzzy logic is a whole other thing, but in a traditional programming language, in a procedural programming language, we would maybe try to do something like this, like if it's a chair, then do something. But the problem is how you know that it's a chair in the first place, okay? And the way that we do it, and one potentially very effective way of doing this, is using neural networks. Neural networks are pattern recognition machines. Neural networks are actually extremely simple. They can get very complicated, but the basic idea is very simple. And I'm going to do my best to explain how neural networks work in the next couple of minutes. Okay. The main points here is that neural networks train incrementally, they're resilient to noise, and they can recognize new patterns that they haven't necessarily been trained on. Neural networks can also do a lot of other things like create new patterns or extrapolate patterns, but that kind of rests on the basics here. So I'll give you an overview of the first iteration of the neural network that was ever invented, which is called the perceptron. We usually use this kind of a graph notation, which means that there's 3 inputs and there's 3 outputs. And an input, a node can be activated or it can be not activated. The idea here is that you attach weights, which is just a number, to these edges of this graph. And when you have an input, you multiply it by its weight, and that goes into this node. And then you see if the weights that came into it go over this certain threshold. In this diagram, the threshold is 0.6. So in this example, the number is not above 0.6, so nothing happens. The output node is not activated. Now, if we take something where the weight goes over that threshold, then we say that that node is activated. Now, you can also have inhibitory weights, which is very interesting and important. You sum those up, you get 0.5, which is not over the threshold, so you do not get activation, even though this node earlier was able to activate the output by itself. And the goal here, really the point of this, is that by changing these weights, you can change the associations of the inputs to the output. Okay? If you take one thing away from the idea of neural networks here, it's that this is a flexible way of associating some arbitrary pattern with some other arbitrary pattern. All right? If you're curious about more about that, I'd be happy to talk to you more about it afterwards. But all this is for, in this context, is for associating a pattern with another pattern. And pattern recognition is not only fundamental to language, but it underlies everything that we think and do. At least that's been my observation. I think that George Lakoff is really right on the mark with regards to that, with regards to the role of metaphor. What I've come to learn is that metaphor is a mapping, which itself is a metaphor. You could say that this use of this pattern to represent or to refer to or to point at or to maybe even cause this pattern is a metaphor. It's just this mapping of states to another state that then can usually when we talk about a metaphor or a pattern, can be extrapolated. So you can learn one pattern, you can learn one association, or perhaps a set of associations, and you can see the commonalities between them, which itself is a pattern, and then you can extrapolate that pattern and apply it to new inputs. So that's one of the bullet points about the uses and importance of neural networks, is that you can train a neural network like this to correctly recognize inputs that it's never seen before. So when you talk about the chairs, part of the problem here is that there's actually a lot of information there that we take for granted. There's a ton of information. We can't even really see that fourth leg, but we know it's there for all kinds of reasons, and we've had to learn that over quite a long period of time ultimately. Okay. and I just thought of this earlier too, which is that when we start observing patterns, it's really natural for human brains to start to extrapolate them, and that's actually why we're all here right now. I mean, I was just like thinking over and over again while listening to these fantastic presentations, as well as watching some of the older ones online, is that the reason why we're making languages is because we start to see how the other languages that we've encountered work. We start to see how they work, and we start to detect these commonalities and detect these patterns, and we just really want to test out those ideas by making new ones and extrapolating those patterns. Okay, so this is the LR cubed, or Little Red Riding Hood example. All right, bear with me. Okay, on the left is inputs, and on the right is outputs, in this case, behaviors. So this would be like if you wanted to create a Little Red Riding Hood robot. All right, so say that the inputs are big eyes, big ears, and big teeth, and the appropriate behavior is to run away and scream and look for the woodcutter. Now, in a traditional supervised network, what you do is you train first and then let the thing go and see what, if it does the thing that you want it to. So if we were doing this as a supervised network, we would train this network first. And training just means that you present the input, the desired output, and then using one of several potential algorithms, the weights between them are adjusted in such a way that in the future, this input pattern will cause that output pattern. I know this is like such a glib overview here, but okay, similarly, you can have big ears, big eyes, friendly and wrinkled, and then you want these behaviors. And lastly, presumably woodcutter behaviors. Flirt. This is not my example, by the way. This is from a fantastic book that you must read. If you have any interest in neural networks, read The Mind Within the Net, Geist im Netz, is the original title, by Manfred Spitzer. It's by MIT. It's published by MIT Press. It's an absolutely fantastic book on neural networks. I highly recommend it. I should have brought mine with me today, but okay. So what's going to happen here is that you can train the network on these three sets of conditions and to get the desired effects. All right. Now, when I said that a neural network can handle novel patterns, that means that these weights can be adjusted in such a way that that if you get just friendly and handsome, you can still get these desired behaviors. Okay, just because the numbers of the weights are changed in such a way. An example in this case would be that handsome, since the only thing that handsome is ever going to refer to is the woodcutter, this can be very highly associated with a high weight, like 1, with these desired features. That means that anytime this goes off, you're always going to get those outputs. All right. So that would be similar to saying sittability, like the ability to sit in something, is a very highly weighted feature of chairs. All right. So that's why we're able to look and go all the way back to this thing. Like if you didn't see somebody sitting in that and you couldn't tell that it was like sittable, then you probably wouldn't think chair, right? Okay, but once you see somebody sitting in it, that feature is so highly weighted towards chair that that's naturally what you think of. Okay, so that's exactly what's going on here. And again, this is so glib. I mean, this is such an incredibly simple model of real neurons and real brains. Okay, but even something that simple is still capable of producing at some very high level the kinds of behaviors that we're interested in, that we're talking about. This shows something called the hidden layer. And the reason why I include this slide is for, it has to do with Plato, okay? Because when you start to incorporate more layers, what you're doing is you're incorporating added levels of abstraction, hierarchical levels of abstraction, okay? What's gonna happen here is that if you just forget the right-hand column, and you train your network, well, I shouldn't put it that way. If you train the network like this, and you just are not really looking at the middle column, and you put your input features and your output features, and you train the network like this using a algorithm called backpropagation, or error backpropagation. What's going to happen is that naturally, only by the mechanism of the algorithm, these intermediate nodes are going to start to refer by themselves to these things. So these words that are actually labeled on there, those aren't words that we, the creators, have applied to those nodes. These are just like concepts that the network itself will start to use those nodes for. Okay? I feel like this might sound dogmatic or something, but trust me, this is actually what happens. And so the reason why this is important is because now this node alone can refer to the concept of woodcutter. And that concept, if this was activated, then these behaviors now would be activated. And you can just start to create immense chains of this activity. And in my opinion, that is essentially what is going on inside all of our brains right now. There are details. But the point here is that now this is detached, this is decoupled from the exact nature of the inputs. Okay? So now you can modify what the features of woodcutter are. You know, if the woodcutter had plastic surgery or something, or then these weights would have to be modified. But these inputs no longer have to be directly connected to the actual behaviors. And similarly, other output behaviors could be attached to woodcutter. Or if you found out the wolf was actually your friend, then its behaviors could be modified, but it would still have the same input features. Okay? So this degree of abstraction starts to create, in my opinion, the cause of why Plato postulated things like forms with a capital F, the way that we transcribe it with a capital F. The idea of abstractions as actually existing out there, and in my opinion, that's a side effect. That's basically a side effect of the way that neural networks work and the way that our brains work, which is that now that we start to have potentially an individual neuron, more like the clusters of neurons or columns of neurons, that refer to some kind of concept, the neural network has no way of distinguishing between an input that is outside of your own brain versus one that's inside of the network itself. Okay? And so what I'm trying to say is that now this neuron in the middle, this node, can start to be an input by itself and can start to lead to the kind of illusion that this concept is actually sort of out in the world. I don't know, this is my hypothesis. So now if we go back to the Dawn chorus, these devices, what I'm doing here is associating an input pattern of senses. This is a photocell, that's a little microphone, with an output behavior, which is the speech pattern. So this right here encodes a speech pattern. The way that this works, you'll see that there's 8 nodes here. So each pair of nodes is a tone. So it's a 2-bit space for tones, which gives you 4 different tones. And then a sequence of 4 of them. Okay? So using 8 bits, you can encode their entire vocabulary of 16 words. Or, sorry, 256 words, thank you. To do the 8 power 256. Okay, so they have a 256 word vocabulary. What this means is that similarly, these encode light and sound levels, okay? So like if it was completely bright, if you were shining a flashlight directly in the little photocell of this thing, it would be 111. All right, that means like maximum brightness. Same thing with sound level. So what this means is that if you have maximum light level and maximum sound level, okay, that input would be associated with some word, some speech act on the right-hand side. And you can encode basically any combination of these levels. If it's sort of average brightness and really quiet, then they would theoretically have, or potentially, have a word for that. All right. Now, I said earlier, they start out, the way that this process works, they start out with just random words. Each one of them has a completely independently random speech act, a word, for any particular stimulus. It is through, where the language actually emerges from, is through the repeated application of teaching of one of them saying bright out loud, and the others being like, okay, associate this like highlight level with the word bright. And every time this happens, the weights between these nodes are changed incrementally, slightly. So it happens over time. In practice, it can be as quickly as 5 trials. What this diagram is showing is that each highlighted bank of bits, this is basically binary notation, means that they were the one that spoke, that got the stimulus and taught the others their word. And you can see at the beginning, at trial 0, they all have different bit fields, different combinations for their word. Okay? And gradually, they change in such a way that by the end, in only 4 trials, they now have all the same sound, speech, the word, the same word for this particular stimulus. Okay? Does that make any kind of sense? I'm like, okay. Oh yeah, I already went through that. Okay. I think that actually covers everything that I had wanted to explicitly talk about. So I want to show the video one more time. We can start to look at what's actually happening here. This is me stimulating one of the devices with a flashlight, or with turning the lights on for the whole room. At this point, they all have different words or competing words. And they're still learning now. You can see in that final example where they've actually started to converge on the same word, the same combination of 4 tones for that particular stimulus. So it works. It can be hard to see sometimes, and it takes somewhat controlled circumstances to really see it in action because they're going to respond to all kinds of stimuli. So if you walk in front of one of them and a shadow passes over it, then it's going to experience it like a change in state. It's going to be stimulated by that. But that's what actually happens, is they gradually converge on the same sound concepts for some particular stimulus. Okay, wow. Questions?
Right. Okay. I will be right back.
Okay. I think most people are aware that there are some paradoxes of language. And one of them is that even though we supposedly use language to communicate, it's also part of the function of language to be unintelligible to people who aren't speakers. And this happens so regularly that you have to believe that there's something inherent in the way language has evolved, that this is a sort of necessary part of the picture. So I'm wondering what your thoughts are on the emergence through this type of scenario of unintelligibility.
Unintelligibility. Well, I guess you could say that before if you just walked up to these guys, they would be pretty unintelligible. You wouldn't know what they were talking about. But something that I found is that even while I was developing these, it was actually pretty easy for me, because I was paying a lot of attention to them. It was actually very easy for me to start to learn their words for things, because I'm an associator. That's what my brain is doing at all times. So I guess if your question is where does that unintelligibility come from, or I never really thought about it that way. I wouldn't say that, like, if you're trying to deliberately be unintelligible, then there's various ways you can do that, and there's a whole history of that. But I would imagine that, I guess I would think, just off the the top of my head that there would be some intent there, some will. I mean, I never thought of unintelligibility as like an intrinsic emergent feature. So I guess I don't know. I never really thought about that before.
Have you observed? Is it on? I think it's on. Yeah. Have you observed any examples of semantic shift? For instance, a word that means level 7 brightness. Well, one of them sees level 6 brightness, so now it shifts to mean level 6 brightness or something like this.
Well, that could absolutely happen. Now, in this system, the only randomness is at the very beginning.
Right.
T equals 0. However, I think, and this is also off the top of my head, but I think if you introduce a bit more of a stochastic function into the learning algorithm, then you can have occasions where, for no particular reason, one of them started saying a different word for something that was already converged upon.
Right.
And the same process would then take hold, is that if that person was speaking enough, the others would learn that. And over time, the de facto word would now be the new one. And I think that's what happens in human societies. I mean, like one thing that I noticed very clearly with this experiment was that it's all about who's talking the most. Okay, and I think we can all like observe that very easily ourselves. Is if you just want to jam a new word into the world lexicon, okay, you can do that. It's happened all the time throughout history. It's not easy. If you happen to get as popular as Shakespeare, then it can start to happen. Even, I mean, how many neologisms does Shakespeare have?
2,000, something like that.
Yeah, and something like 100-something of them are still around. It's crazy. It's amazing. But that's this process in action, in my opinion.
For what it's worth, I do know some of my AI. I'm curious of a couple of things. One is your input was only volume, but your output is tone. So is that an intentional loss? Because the output has tonal things, not just different, are the tones different volume levels?
Well, okay, so there's two answers to that. The reason why I designed it that way was because I didn't have enough time to do anything more complicated than that. Detecting the raw sound level, meaning essentially sound pressure level, is like the simplest possible thing I could have done. If I wanted to have it analyze the frequency domain, well, I could do that with a Fourier transform and add a whole other stage and a whole other level of complexity. I'd have to totally change my hardware. Probably use a Raspberry Pi to do it. I have to write a bunch of software. So the answer is pragmatic, but it's completely doable. I mean, again, it's a completely arbitrary association. You can associate just absolutely anything you want with anything else that you want.
Second question. I'm wondering whether you've considered using higher-end AI like a support vector machine or having more complex output sounds. Is that just a limitation on your time to do the project, because this was a school project, or a limitation on Arduino?
Yeah, also a pragmatic decision. This is the microcontroller that is on an Arduino. It's an AT Mega 328. Doing a perceptron, which is what this algorithm is like the simplest possible thing you can implement. It's really, really easy. It's one equation. I'm sure you could probably jam a support vector machine on that thing. That would be pretty cool. But this was also the algorithm that I knew the best at the time. Yeah. But also, I mean, really, it was too. I was like trying to test a very simple proposition with the simplest possible network, and I think it was successful. I think it was effective. Which is telling, right? It's crazy.
So on the unintelligibility question, have you done things where you've taken them and like separated them into groups and had them, come up with separate words in the groups and then recombine the groups so that?
So this is fascinating because I think every time I've talked about this, somebody has asked that almost the exact question. It's really interesting. Now I haven't done it myself. For one thing, I only have 4 of them. Maybe you'd still do it. You could totally still do it. Here's what would happen. If you isolated each of them, it would be kind of what would happen with isolated communities of human language speakers. They would just keep going off in their own direction. It would just keep, the same process would take hold. The longer that it happens in total isolation, the potentially less resemblance they would each bear to each other. But now if you brought them all back together, the same process still holds. Okay? And in this case, it's going to depend again on who's talking the most. If one of those cultures, you might call them, one of those cultures just happened to be talking more, okay, the others would eventually learn, like that language culture would take over the others eventually. But then you would get intermixing potentially.
I have two questions then. First one is, did you play with the number of hidden layers, the number of nodes per hidden layer, and if so, what were the results?
So the algorithm that's running on this doesn't have a hidden layer at all, actually. It's just a bigraph. It's just the one-to-one combination. Hidden layers is kind of a tricky thing. Like it's like there's rules of thumb to kind of figure out like how many nodes you should have in a hidden layer. I don't really remember what the rules of thumb even are off the top of my head, but in this case it wasn't necessary. I think that if you did that, what you would probably see, like I would probably do 2. Well, yeah, maybe 2. I mean, usually when hidden layers are specified in a neural network architecture, it's done so with a certain amount of expectation, or at least hope, of what they're going to represent. So that's kind of why it's kind of like heuristic. It's like the way that I might think of it here is that I would think, okay, well maybe you could categorize the world ontologically up into like bright and dark, or sorry, bright and loud, bright and quiet, dark and loud, dark and quiet. So maybe you could have 2 nodes in the middle that would end up, that's a 2-bit, solution space that would give you those combinations of things. I mean, it wouldn't be useful in this case, but that's probably what would happen.
And also, a lot of times when we want to create random behaviors in AI, we use a classifier, right? Could you speculate on what would happen if you use that algorithm instead of the
Well, I technically have to ask which algorithm you're talking about, but I'm not actually an expert on all of them. The use of the word classifier, though, is interesting to me, and I'll take this opportunity to go off on a little bit of a tangent because I think it's really interesting. I talked about supervised learning, but there's also this idea of unsupervised learning, which is actually really a whole other thing, and I was confused by it for a while until I realized that the word unsupervised is like a weird word choice to use for that. But what unsupervised learning is something that we're all very familiar with. If I drew a bunch of dots up on the screen, and some of them were clustered in the top right, some of them were clustered in the lower left, and I asked anybody here how many clusters there were, you'd say, oh, I don't know, there's 2. There's like a cluster in the top right and then one in the lower left. Okay, what that is an unsupervised learning or a clustering algorithm that allows us to just see the similarities inherent in the information itself. So if you took this hypothetical, you just have to imagine. We took this hypothetical drawing and then you converted it into just a table of data of X and Y positions of each of these dots, and then you were asked to look for how many clusters, you'd be like, I have no idea. It's just like I can't parse that list of numbers in the way that I can parse the actual visual representation of it. What unsupervised learning means in that case is just looking for patterns that are inherent in the information. So there's no notion of training in this case. You're just looking for stuff that's already there, looking for similarities or patterns. And there's various ways that you can do this, most of which are fully deterministic, and well, not most of which, but anyways. Now, I guess I don't know how to answer your actual question. Was your question like what other algorithms could I have used to do this?
We can use it as a question.
Yeah. I don't know. I never really thought about it before. This was the algorithm that I was interested in at the time in testing. I don't know. I mean, it would be, I don't know. I think that the data, the input data in this case is not like interesting enough to use like a real sophisticated learning algorithm on, because there's not that many patterns in the data, or like patterns in the way that we think of it. I don't know. Hopefully that's not a disappointing answer.
Well, first of all, this is an amazing experiment. This is really cool. This is incredibly mind expanding. I'm a freshman in college, and this is just incredible to think about. Thank you for giving this. But a question I have concerning the language these robots make is that it seems to be a very reactive language. Like they take external stimuli that they themselves do not produce and classify it like it's like someone looking at the sky saying that's the sky, and looking at the ground saying that's the ground.
Right.
But they themselves don't create action. How do you anticipate that next step? Like
Interacting with the world.
interacting with the world and coming up with words for that interaction.
Right. Yeah, I mean, you could expand this model in to starting to go in that direction. There has been some extremely, I mean, actually a lot of really incredible research taking these kinds of network architectures or conceptual diagrams and applying them to those more sophisticated scenarios. I wish I could remember her name. She's an Australian researcher. I'd have to look it up, but she's done some incredible experiments with moving robots that come up with place names for wares. And we heard of this research. It's really interesting. I want to meet this person. The robots basically can move around, and they emergently begin to just assign names to certain locations that are basically useful for them to help them navigate or communicate information to the other bots, to the other robots. So it's like if you wanted to tell somebody else how to get to somewhere else on campus, it would be helpful if we could use these intermediate place names as nodes to describe, okay, you go to this road that has this name, and then you go left and you go to this other node that has this other name, and so forth. But yeah, I mean, you can take the same process and start to apply it to actuators. So you can use that output layer, or part of that output layer, to encode the movement of motors, or anything ultimately. I don't know. That's an extremely broad answer, but let's talk about it more later.
In regard to the last question and your answer that this model could be expanded, I think I'm missing something in trying to understand that answer. Because human language is generative. I mean, with a finite number of possible components, phonemes in a language, tenses for your verbs, etc., lexicon, we can generate an infinite number of sentences that have never been spoken before, never will be, and we can take a sentence and keep adding on to it and making it longer, theoretically, infinitely. I'm not seeing how this model allows ultimately for a generative experience to result, even no matter how many nodes and how many outputs you add on to it, or how big you make it, so to speak. I'm not seeing where you would be able to have infinitely generative behavior take over.
Right, so you mean generative in the sense of combinatorial, I think. Right.
Yes, and you might even go on to expand that into emergence. I mean, I'm not seeing where emergence takes place, where we go beyond the sum of the parts.
Okay, so, well, there's kind of two things there. The combinatorial thing, I have thought a lot about. Like, one of the projects that I wanted to do that I still would like to do, I don't know if anybody's done it. If they have, I would be more than happy to read about it, is apply this idea to a grammar. Like right now, obviously there's no notion of grammar in this situation. It's purely kind of, in a certain sense, lexical. It's really just associating one thing with another, giving you what we're going to call a word. So if one wanted to make a combinatorial grammar with reusable patterns, the best answer I can give you right now, right this moment, is I have this intuition of how it would work, but I haven't done it myself, and I haven't read the actual research, so I can't say for sure whether it's actually possible or what would be involved. But I really want to do it, or at least like encourage somebody else to do it. Okay. The second aspect of that, was refresh my memory.
Emergence.
Yeah, emergence. Okay, well, so this is maybe a little bit philosophical, but I would say that the emergent part of this, or from my perspective, is the kind of higher level perception of there being a language that has to do with the convergence of the shared meaning. To me, what I would call emergent about this extremely simple experiment is that over time, they just start saying the same words for the same things. I feel like that's an emergent property.
I
think that's debatable.
I certainly would call it heuristic, but I don't know if it's meeting the requirement for emergence. I mean, it's certainly learning,
Right.
but
Yeah.
it seems constrained within its own parameters as opposed to being infinitely generative, ultimately. So.
I think that's arguably true, but yeah, we should argue more about it later.
All right.
Especially if there's beer involved.
You're on.
One quick comment and a question. One way that this could be generative is if you loop your outputs
Recursion. Recursion.
Well, right, so
Recursion.
yeah, that's the next big step.
So if you
there.
make their speakers loud enough for their own audio sensors to hear, or if they flash lights that are visible by their own, that could create a recursive loop. That would-
You're absolutely right. Recurrent neural networks is like the big thing here that's not really, that I haven't talked about at all. Our brains are highly recurrent, and it is my belief that that's what contributes to a lot of the higher level phenomena that we experience. Now, interestingly, you noted something about one unit's own output stimulating its own input, self-stimulus. So that does actually happen, except that it was annoying. So I had to hard code it to ignore its own input. But that was happening. It does get stimulated by its own output, which like in this kind of very simple scenario, really creates an undesirable or unproductive feedback loop where it's just going to keep squawking and nothing's going to really happen. It really kind of defeats the purpose. So I like hard coded it to not do that. But that's really interesting. And
You're sounding like the nuns that taught me at Catholic school.
how are we doing on time?
This is more a comment than a question, but I mean, there have been a lot of questions about how you could get your robots to display, feature X of language, which they don't. I kind of feel that one of the things which is missing is any sort of functional pressure on the resulting system.
Right.
Kind of long-term, maybe they all have to come up with the same word for every stimulus, all of them, and that's stable. They all just go do for everything, and that's not very functional.
Well, sure,
It's
right,
stable.
exactly,
So,
yeah. And when I started working on this project, I knew from the beginning that like I wasn't particularly interested in, for the purposes of this, particularly interested in doing like a whole larger scoped experiment about some of those aspects, like one experiment that you could do, which I'm pretty sure has been done in many various forms, is tie the language use to something like needing to get food. Would be a pretty great starting point for that. That does give a constraint, a functional constraint for how that language emerges and what it's used for. I mean, natural language is used for things. It doesn't just exist in a vacuum. Except in this case, it does kind of exist in this vacuum. It's purely part of a very specific controlled experiment. Right?
Quick question. You said they converge sometimes in as quick as 4 trials. I was wondering, what was the longest or the most amount of trials it took for them to converge, and did they ever have trouble converging?
Well, so if it all comes back to how often any one of them is speaking. If the distribution is really flat, if they're all speaking equally, then it's going to take longer for there to be any kind of convergence. Okay, and what can happen with simple neural networks like this, and one of the reasons why neural networks of this architecture are not really used for anything these days, is that you can get into these oscillations where it overshoots a mark in either direction just repeatedly. That was a common problem with perceptrons. And that would definitely happen in some scenarios. If all of them were speaking kind of equally frequently, then you might run into problems where one word kind of just keeps flipping between these two options because it's kind of like targeting this unachievable middle mark, if you know what I'm talking about. But so that can create a kind of like endless situation conceivably. Other than that, I mean, I haven't measured any specific like lengths of time for convergence to happen. Not specific.
Thanks so much.
Okay, thanks for everything.